Okay, when the speakers are 20 centimeters apart, they have constructive interference. That's the main idea here. Interference. When they have constructive interference, that would mean that the crests of the wave from each speaker, from speaker 1 and speaker 2, are in alignment, creating maximum intensity sound. If we move the speakers 40 centimeters apart, you get no sound, which is perfect destructive interference. Okay, and we have, if you want to see in between the red sound intensity wave of these two waves going back and forth, the red wave, when it's flat in the middle right there, you don't hear any noise because the crests and the troughs of the waves align, and then you don't hear anything. And then when the crests align with the crests, you get the maximum. Boom, there you go. And in between, you're hearing noise, but it could be the intensity of the sound could be decreasing or increasing. And if you look at this peak right here, it sounds up here and then it decreases to the middle, and then if it starts down here, the sound will increase until it gets the middle line. So it's either at maximum decreasing to nothing, or it's at a maximum increasing to nothing. And we have two equations to deal with this situation. Well, first we can clearly state at 20 centimeters, constructive, 60 centimeters destructive. We have two equations to deal with this. The constructive interference, we can use the equation for the phase change, and we use that because we know on this side of the equation we can use no unknown variables. So that takes care of one side of the equation. On the other side of the equation, this stuff, we know the separation condition, and we don't know the inherent phase difference between the waves, but it just know that it is common to both, because this delta takes into account the initial phase of one wave and the initial phase of the other wave. And the change takes both of them into account because it's just the difference between the two. So that's common to both. And so if we can solve for this equation in terms of that, then it will be in terms of only the unknown wavelength, which is actually what we're trying to solve for in the first part. And we can use the other condition. They have destructive interference at 60 centimeters. And so we can convert that to meters, 0.6 meters. And so we have this equation with the 0.2 meters, which is 20 centimeters, and it's put into one equation, the only unknown here. We're going to solve for phi naught in terms of lambda. And then with the other one, we're going to also solve for phi naught in terms of lambda. That's the goal here. Because when they both have lambda in the equations and they're both equal to phi naught, we can just set them equal to each other. Like, it's going to be phi naught is equal to one thing in terms of the wavelength, situation 1, where they're 20 centimeters apart, and that's going to be equal to the other equation solved in terms of the wavelength at the 60 centimeter separation, to give you an idea of where this is going. And then we can set, once they're those, we just like, okay, ignore that. Now we just have these two things equal to each other with just wavelength in them. So let's algebraically solve for the wavelength. And that's what we're going to do. But first, like, let's say that when the spheres are spaced 0 centimeters apart, they are in an in-between max constructive and max destructive. It's going to be in between. So when they first get to a separation of 20 centimeters from 0, we're going to say m equals 0 for the m integer of 2 pi. And this is because the 20 centimeters, we're going to assume that it's the shortest distance of constructive interference. And likewise, we can use m equals 0 for the other equation here. And if we use that, then, well, that just gets rid of our m's for both of these, and we can just get it in numbers, no letters on this on these right sides of the equation here. No letters if we plug in for m. And we can, so we're going to also assume the other m is 0, because this is the shortest distance for them to interfere destructively. Remember, we said at 0, they're in between, up to 20 it's max, and then to 60 centimeters it's so it's decreasing from 20 to the separation of 60. And this looks like the situation here. So if we look at these leading points, the starting points of these two waves, then say like at 0, they have, say at 0 position where the waves meet, one's coming from back here, but well, if they're both at 0, then they could have an inherent phase difference, making their troughs and troughs not line up with each other. So what we know is when they're moved into position here, boom, crest line with crest, we get maximum interference. And then when they're moved, the minimum distance it takes to get to the destructive interference, we can see that the sound is decreasing to 0. And if you kept going, it'd be increasing up to maximum again. But okay, back to 0 here. That's where they're at 60 centimeters, and just in between. The idea here is that in between they're increasing and decreasing, so that's what this illustrates. And this is the two waves from each individual speaker, like stacked vertically on the paper. But in the physical situation, these are on top of each other like this. If you can kind of see the red underneath here, they're going like that, you know. Maximum, move by pi, O, max destructive, canceling out completely, max constructive. And that's similar to this right here that we said. Okay. Depending on the positions of the speakers, they can change their interference, and they may also have an inherent phase difference, but it's common to both, so let's eliminate it. The algebra here, once we plugged in our m equals 0 over here, this is 20 centimeters, we plugged in for delta x. Okay, and then simply solve for phi naught. Our other setup, destructive interference. We have our m equals 0 plugged in right there. M equals 0. And then 0.6 meters for delta x. These are all, and then if you see here, then this is 0 times this 0 plus 1/2 times 2 pi, that just becomes pi. And then let's solve for phi naught once we get to this stage, because we just have lambda here, and maybe we can do something with that. Okay, so algebra here, you know, subtract this term over to the other side to here, and take out the common multiple of pi. And that's what it looks like, nice and simplified. And so we're close to finishing this one, like when we have it, like I said, when they both are in terms of lambda, then we can just algebraically like combine lambda by multiplying both sides of this equation by lambda. That's going to get rid of it on this term, get rid of it on this term, leave a lambda right there. And this wavelength is going to be common to both the speakers as well. They're going to share the same wavelength. And we find that is 80 centimeters. Okay, and the next part of the question asks us not what the wavelength is, but if they continued moving past the 60 centimeters, then when would they interfere at a maximum again, which is going to be a wavelength separation, actually. So if you found that wavelength of 80 centimeters, you could add it to the 20 centimeters from where it was maximum the first time, and then adding a wavelength to that, like this here. If they're both lined up like that, then adding a whole wavelength is going to be like half wavelength, boom, whole wavelength, and they're going to interfere constructively again. And again, this is the one speaker physically moving, and the other speaker is stationary. But this is just the representation what the particles in the medium, which is the air, this is the displacement of those particles, and that coincides with the noise that you hear because it makes the pressure in your eardrum. And so if we move a separation of one wavelength, boom, one wavelength, we can get the maximum interference again. So adding 20, the initial separation to 80, you get 100 centimeters. Okay, so you know that at the end, if you get 100, you got the right answer. Okay, so for part B, the problem tells us that it has constructive interference because the sound intensity is a maximum. Okay, that's what the question says. If the distance between the speakers continues to increase, at what separation will its intensity again be a maximum? Okay, so like I said, we know this is going to be one wavelength, and we found the wavelength, and it's one wavelength from 20 centimeters. But we can see in our setup here, we have a nice setup for constructive interference. We don't know what delta x is. That's what we want to find. If the distance continues to increase, then what will the sound intensity be? Again, be a maximum. So that's our maximum right here, that information. We don't know what the inherent phase difference is, but we can easily plug this wavelength that we found before into using the simpler equation from part A. You can use either equation, but use the simpler one. And the simpler one from part A looked like this. I can show you again. We just solved each of those in terms of phi naught. In terms of lambda, actually, but solving for phi naught. And this one, it's very slightly more complicated, but this one, we can just plug in that number and do that division here. And we do it, and 0.8 meters for the wavelength, and we get the inherent phase difference of negative pi over 2. And so like I said, we're just going to solve for delta x here. We found the wavelength. We're just going to solve for delta x. We found the wavelength. We just found the inherent phase difference using the wavelength plugged into our equation. And we're going to use m equals 1 here because 60 centimeters is definitely going to be the next time after the first time that they have maximum interference. So the first time that they have maximum interference, we plugged in 0 there. But adding 1 to it, we can use it, use m equals 1 because we used m equals 0 for the first distance of constructive interference. And for each one after that, you would use like m equals 2 for 2 wavelengths past the first time that they constructively interfered. M equals 3 for the 4th time. and so on. And so I hope you understand that m equals 1 here, because this is the first time that they're going to interfere, but that's after this second time, so it's like it's a little bit confusing, but you use 0 for the first time actually, and 1 is going to be the second time, and that's why I said, yeah. We can just solve for delta x once we have all those other numbers in that equation here. And then that's going to be (100 centimeters). And that makes sense because we said the wavelength was 80 centimeters. And one wavelength past 20 centimeters would take a distance of 80 centimeters past 20 centimeters. So it would be 100 centimeters when they next constructively interfered. And I want to just mention that this inherent phase difference means something physically that's going on. Okay, negative pi over 2 means that if you have waves starting from the same position like this, and you did a phase shift of negative pi over 2, that would actually mean that you take the whole wave itself, take this whole little wave, and shift it up pi over 2. This is the unshifted. Take this origin here, shift it there, so that it's going up right here. And you shift it forward even though it's negative, because the displacement of the medium, of a particle in the medium, since it uses the sine function, what you want to do is set the stuff inside the sine function equal to 0. And that's because that's how the sine function works. If you have sine of 0, that is 0, so that would be the origin. But if you take that stuff and you subtract pi over 2 from it, then it's the same as the opposite. So you're shifting the whole thing forward pi over 2. And instead of shifting it back, which is a little confusing, so I thought I'd clarify that. If it's negative, shift the whole thing forward. And so you can see that when this thing's shifted, it starts at the minimum and then it goes up. Okay, that's pretty clear. And so, like here, let's talk about this. When it's here, you would say that there's no like phase difference between these two, but like I said, the phase difference over here is pi over 2. And then if we move this one just like that, then we have made those phase differences a phase difference of pi over 2. So that's what we said for this problem. We said that the inherent phase difference is negative pi over 2. So that corresponds to this. And 20 centimeters, see if each of one of those increments is 20 centimeters, then 4 of them is 80 centimeters, which is the whole wavelength. So you could think of that as being like 20, 40, 60, 80, and that's just a nice wavelength right there. And so if you shifted one of the speakers, so that's the speakers so that would be the speakers at the zero position. And then if you with the inherent phase difference, and if you moved 20 centimeters, like we said, 20 centimeters, then that'd be like, oh, let's take this source speaker that starts at this line right here, take the source that starts at this starting point, and let's take the source and shift it back just a little, 20 centimeters. And so that's the situation we said it's in here. And if we do that, what should happen? Well, they should constructively interfere because they have an inherent phase difference of negative pi over 2, and in the problem they're separated by 20 centimeters. So if you shift it 20 centimeters, you do get maximum constructive interference. And if you shift it 60 centimeters, that's a difference of 40 centimeters, which is half a wavelength. Boom, boom. And you can see, that's perfect destructive interference. Like the equation says, the sound's intensity as the distance between the speakers is increased, reaching 0 at separation of 60 centimeters. Let's just remind us that that is the two waves interfering, making 0, making no noise. And so, and then we move it another, then we want to move it how much more to get another maximum constructive interference? Well, we move it 20, 40 centimeters. And that corresponds to a total of 80 centimeters, which is why at 100 centimeters they are again at maximum constructive interference.